so now that I advertised, I can get to work. So almost like I'm doing a commercial. Right, so last time we introduced this definition of a robust sublinear expander. We proved the lemma that you can find them in any graph, and there were some caveats that I'll not get back to. I'll just stick to the regime being log n or more. And we also saw one application which was a bit quick, but also nice and short, to finding these topological cliques, where this whole story started in the 1990s. So for today, I want to show you a different application. But actually, there was one thing that I did want to point out, because there were several questions last time on that point. And this is that I was using that these things are 1 over 4 log n expanders, according to our just vertex expander definition. Right? And the reason for that is that you never want to take epsilon here, really, which is smaller than 1 over log base 2n. Because if you choose it to be that, you get n over 2. You don't really want, in the usual definition, we don't expand sets bigger than that. And also, even with this definition, you don't really want to expand bigger sets. Things will start to kind of grow too slowly. So this is a 1 over 4 log 2n expander. And also, as some people noticed at the end last time, is we didn't really use the full power of this for this topological clique example that we did. We really just used the vertex expansion. So today, we'll see an example which does actually care more about this. And also, if you wanted to push this and kind of not pay these logs, then you would need to start using some sort of robustness conditions for that problem as well. Very good. So for today, I want to show you a slightly weaker version of a recent nice result, and it's concerned with finding rainbow cycles. But before starting with that, so since there is no lecture on Ramsey theory today, I think it's quite appropriate that we have a lecture on anti-Ramsey theory. I kind of think of this problem, so it's a general question of Kivash, Mubai, Sudakov, and Verstraat, of this rainbow to run problems. So what they're asking is, you can pick your favorite to run problem or extremal problem, and you can convert it into this, what I like to think of as a slightly anti-Ramsey setting. So what they're asking is, well, in usual Ramsey theory, it says that in any large structure, you can find a well-organized substructure. Great. And so how about if you want to find a very disorganized substructure? Now, of course, let's work with the standard example. So you have a colored graph, you want a clique. Of course, it's not possible to find a kind of crazy anything other than a clique, because you could be a monochromatic clique to start with. Right? So you need to make some sort of chaos assumption on your big graph. And then what these questions are asking for is that chaos assumption is to ask that the graph is properly edge-colored. And then you want to find an ultimate chaotic object there, which is that it is rainbow, meaning it doesn't reuse any color. So the exact opposite of what Ramsey wants. It wants monochromatic things. This wants crazy stuff where you don't reuse anything. So definition, proper graph, proper edge coloring. Is just a function from the edges of our graph into some color set such that each color class so chi inverse of I is a matching. Or if you prefer, there are no two adjacent incident edges which share the same color. Okay? So this is what I like to think of as a slightly chaotic assumption on the coloring. It prevents you from taking a monochromatic coloring, for example. And it actually pops up in a lot of different places, which is why this has been used and has some quite nice applications. So maybe the most general one, and the one that you will also see in Liana's talk tomorrow, is for Cayley graphs. So Cayley graphs come with a very natural proper edge coloring. So you can use various graph theoretic tools to actually argue and say some nice things about groups or whatever or just the Cayley graphs themselves. So another one comes from geometry. So for example, if you think of a unit distance graph, so this is a graph where you put a bunch of points in a plane and you join them if they're at distance 1, then this is almost proper. Technically, there could be 2 edges. The coloring is you color according to the direction that the edge goes. Right? So all parallel edges should get the same color. So this is almost proper because at every vertex you could have 2. And then through this, you can actually use some of the expander machinery and say something about some geometric problems, namely concerned with the unit distance question of Erdős dating back a long time. So these are just 2 examples. There is a third one which goes into coding theory, and which I'll not explain more, but actually the result that I'm going to tell you actually through all of these 3 connections actually says something interesting, actually very interesting in coding theory. It essentially solved an old question that they cared about for a while, for quite a while, and it did something very nice in geometry, and it's also doing some stuff in Cayley graphs, but not really the problem that, well, it's saying something about additive dimensions, so it's also doing something there. Very good. So the second definition I need is what I mean. So this definition is defining a little bit of chaos. This definition is defining full chaos. So colored graph, a coloring of a graph is rainbow if all edges get distinct colors. So now what Kiváš, Mubai, Sudakov, and Verstraete asked, so this is, I think, 2006, although there were some examples of the same question, specific instances before. So they're asking, pick your favorite to run problem. Let's say we are looking for a cycle in a big graph. So how many edges do you need to have in an n-vertex graph to find a cycle? So this is a basic question that if you think for 3 seconds what I'm talking about, you'll realize that it's easy, and the answer is n. Right? So trees are a cyclic graph, so if you have n edges, you will have a cycle. And you can convert it into a question which asks, suppose that my underlying graph is properly edge-colored, and now I'm asking for a rainbow version of the same structure. So how many edges do I need to have in a graph so that every proper edge coloring of it contains a rainbow copy of some structure I like? Okay, so that's the general rainbow to run question they raised. And in particular, this cycle one is the one that we'll talk about. And it's at least one of the 4 authors told me that this was the main question they were interested in when writing that paper. So here's the question. How, I think it's maybe even a conjecture, but how many, I definitely conjecture it, but how many edges you need in an n-vertex graph to guarantee that in any proper edge coloring of it, there exists a rainbow cycle. So it's due to Kiváš, Mubai, Sudakov, Verstraete. And they were motivated by one of these 3 applications I mentioned, so the additive one, and but as I said, it actually found some pretty surprising and cool applications. But it's also a very, I think, cute and natural question, and it's also sort of became in the area a sort of benchmark problem for these sublinear expanders. So there has been quite a lot of papers which were progressively improving the upper bound on this result. And they were switching between using sublinear expanders and homomorphism counting, which is a method that Oliver introduced. So the current best one is on the sublinear expanders, but they alternate. So we'll see. Very good. So just first observations. Also, I just want to stress that you can ask this same question for your any to-run problem you like. And very often you get interesting ones. Quite a few were studied. So if you want to find some question, pick your favorite to-run problem and try to see what happens if you do the rainbow version of it. Very good. So just an example to kind of maybe clarify exactly what is going on and to show that the answer is a bit different than this silly question about finding a cycle in an uncolored graph. So we do know that you need at least n log n edges. And the reason for that is the hypercube graph, which I forgot to mention as a question some time ago, but it's a kind of prototypical example of these sublinear expanders. And it actually has a nice proper edge coloring, well, the natural one. It's also Cayley graph, so it also follows in that bucket there. So if you take the hypercube and you color all the edges that go into the same direction in the same color, I claim that you do not have a rainbow cycle. Right, so let me do a picture with a 3D thing, if I'm capable of drawing a three-dimensional hypercube. Right, so I want to color all the edges that go in the same direction, in the same color. Right, so that's a proper edge coloring, because each direction consists of a matching. And also, why do you not have a rainbow cycle? Well, suppose that you start at some point and you follow any direction you like, let's say red. Let's say we followed red. Then you are stuck in this layer of the hypercube up until you use a red edge back, right? Because the red edges make a cut between the two parts of the hypercube, and you started on one side and you're on the other. So in order to wrap back here, you need to use another red edge. Okay? So this tells you we need average degree to be at least log n. So note that this is essentially equivalent to saying you need 1/2 n log n edges, and I think this is base 2 and should technically be a floor. And there is some things like that. And actually, as the first exercise for you, try to figure out of an example that does better by a constant factor there. So this was done already in the original paper, and the best construction is a tiny bit constant better than this. So exercise 1 for today, prove lower bound of 1 plus epsilon log n for any epsilon you like that's bigger than 0. Okay? So I think theirs is something like 1.1, and this is the best construction. If you beat that, I would be very interested, but even just getting 1 plus epsilon, I think, is a fun problem and nice thing to think about. Very good. So that's essentially the best lower bounds we know, so log n. So note that in the usual world, that would be 2. So if you have at least n edges, that corresponds to average degree of 2. So it is growing. It is a bit bigger. And after a long sequence of works, which I will not list now, but I will mention in the notes, the state of the art is that big O of n log n log n edges suffices. Yes. I'm missing an n, I see. Sorry. Yes, thank you. OK, so we are only this log n off. And this is a recent result. And it's kind of heavily using that definition there, and lots of different stuff coming from that. So I'll not show you the proof of this, because I'd probably need to spend the rest of the course doing it, and even then is a question. So it's using those things, but it's really kind of involves quite a few technical and clever extra things. So I want to show you a slightly weaker result, which still illustrates lots of the main ideas, and in particular illustrates quite a lot of tricks that are useful generally when you play with these sublinear expanders, and which does a little bit worse. So we'll prove a log squared bound, which is so if you want average degree is log squared, so n log squared. And I'll also add myself a couple of logs, just so I don't need to worry about certain points in the proof. You'll see that. So one of the logs is secretly the same log as there. The other one we know how to get rid of. That will be your exercise after you see the proof. But makes things a little bit more technical, and I don't think it's necessary. So this result was known already before this. So it was, and even without the log squared. And without the log squared, it was proved with homomorphism counting. And with the sum power of polylog log, it was proved using expanders as well. So the proof I'm showing is drawing lots of similar ideas to what the paper of Tomon did, and then a later slight modification of it by Wang. But it's more translating various ideas from here to just how they simplify when you actually have a little bit of extra space. Just so I don't spend 3 lectures doing this. Very good. Any questions about any of this? OK. So let's start. So what is the first step that we should do? Maybe I want to keep that for a bit longer. Anyone has a suggestion? Hint is name of the course. Perfect, yes, precisely. Use that lemma, right? So it's perfect for this problem because the only thing you know about this graph so our setup is you are given a properly edge-colored graph with this average degree, and we're looking for a rainbow cycle in it. We don't care about the length. It just needs to be rainbow. So if you use this lemma, you lose nothing. Why? Because if you plug in here log squared, and even if you plug in log n here, then this log and this log cancels, and you still get the average degree, which is at least the same function in terms of the size of your smaller graph that the big one had. Right? So it's completely free to pass to one of these things. So let me do that, and let me just assume that our initial graph was one of these robust sublinear expanders, so I don't have this n and m issue that there are 2 graphs that are floating around. So for the proof, first step is use the pass to expander. Lemma to pass to an RSE, right? Very good. So let me just assume, so log, assume our initial graph G. G is this RSE. So let me also set up a notation, so some notation. So the number of vertices is n, the average degree is d. So we know that d is at least, let's say, 10 to the 7 times log squared and log squared. Good. So this is just kind of setting up various things that will be showing up. So did I forget one? Ah, yeah. So we have a proper coloring. And let chi be the proper edge coloring. Right, and our goal is to find a rainbow cycle. So this is actually a pretty sensible thing to try to do, because if you remember, it was pretty easy to find long cycles in expanders, and actually generally finding cycles they're pretty good at. So this is, and here the issue is that this cycle needs to be special. It needs to be rainbow. And so the question is how exactly we are going to ensure that point. Good, so let's try a first kind of naive idea. So let's forget about finding, forget for a moment about the rainbowness property. Then kind of natural thing you could try to do is, well, pick an edge, right? And then do this diameter bound argument that we did before, right? So grow around, grow around, grow around. Eventually you reach half, then do the same here, do the same here, do the same here, etc. And eventually these two intersect, you find a new point, you find a point there, and then you have walk there, and you can close the cycle. Right? So this is perfect strategy, modulo that we forgot about the colors. Right? So I claim that actually part of the strategy still works pretty well for the rainbow cycles with our definition there. And it's going to be part of the proof, so let's see it. So, yeah. So you don't, so this is, so I can spell out that computation somewhere. Where do I spell it out? Maybe I can actually just do it here, right? So G, our big thing, had log squared log log. Right, so this is n. So you're perfectly right that this log n cancels with that, right? But you still get this log. And since h is our new g, this n is always bigger than h, so this is actually bigger or equal than, and whatever we had 10 to the 7 somewhere here. You still get 10 to the 7 log size of h squared, and then this log log also in terms of size of h. So this is kind of telling you that this is being a tiny bit wasteful when you're working with the log squared, but you don't really get any much. You should actually use the 1 over log squared potential if you want to work at this point, and then you don't really get anything much better in terms of expansion properties. But you are correct. There is a step here that I was slightly hiding, and that often happens. So for this type of problem, you really lost nothing when you did this step. Everyone happy? Good. So let's get back to our growing beans or balls or whatever that is. So, right. So the difference compared to the usual problem is we want to grow using in a rainbow way. So we want to look at rainbow neighborhoods, right? So we can still kind of go here and then expand once. Then whatever we get is reachable by a rainbow path. And then we see, OK, who we can add to this, like who we can join by an edge so that there is a rainbow path. We can keep doing that. So let me define this notion, since we'll be playing with it. So the rainbow neighborhood of radius I around the vertex V, and using a color set C prime, so that will be important in a moment, is the set of vertices reachable by a rainbow path from V of length at most I, and using only colors from C. C prime, I guess I call the set. Right? So it's the usual ball, except instead of being reached by any path, I want you to be reachable by a rainbow path. So that's the only, well, I want the path to also use our special set of colors, which we'll get to. But so far, assume that this is all of the colors. So indeed, if you try to use this property, so this lemma we will now no longer need. We already passed into an expander. We got the degree there. The expansion property we will need. So how do these rainbow neighborhoods, when you include all the colors, so forget about the colors, the subset of colors for now, how do they grow? Right? So suppose we have the ith rainbow neighborhood. And let's look at all the edges that go out. So for now, I'm just looking at the neighborhood of this. I'm ignoring the fact about rainbow stuff. Now, for every vertex in this original rainbow neighborhood, there was a path of length at most I that was rainbow and that went to the origin, to our vertex V. Right? So if this new edge is not in one of these colors, then this vertex gets added to the new neighborhood. Okay? So let me call the edges that you don't get there blocked. So this one cannot happen because of proper, but these two could go out. So these two are not good for us, right? I mean, they might be because of some other path, but at least we fixed some path and we're playing the game that way. So let me define this. An edge is blocked, and it's always going to be with respect to some rainbow neighborhood, but I'm not going to be writing it usually. If there is no rainbow path, this is not going to fit. From its vertex in, call this U, in U to V of length at most I, and not using the same color, not using its color. So also it should go out of the U. I'll add that thing. But so this is kind of messy to write, but the picture really says everything. So it's any edge that you could use to grow your rainbow neighborhood is really this. So let's continue here. Not using the color of the edge. And this guy should go from U to outside. Right, so I'm really looking at the edges that go from this set to the neighborhood of this set, so not within the set. So just edges that kind of could potentially work for us to extend the rainbow neighborhood, but they don't because we don't have a good path that already led us there. Make sense? Okay. So one observation is that every vertex in U, so well, I'll call that U, but okay, let me see, has at most I blocked edges incident to it. Right, so this was this picture with the path. If you are a vertex inside of this rainbow neighborhood that we want to expand, it is a distance at most I in this. There is a rainbow path of length at most I from it to the origin. So these are the only colors that could ever possibly be blocked. And because we are a proper edge coloring, they appear at most once at this vertex. Right? So I'm not saying that this other vertex doesn't also have a rainbow, a red forbidden edge, or a blue if we also had, well, this is bad in the, if you also had some other rainbow path that joins you there. I'm just saying that at every vertex, you get at most I bad edges. Right? And what do we do with bad edges in these type of robust sublinear expanders? We forbid them, right? That's the whole point that they are good at. So let F be the set of all blocked edges. Now, what is its size? So let me call this U because I already did at some point, but it's going to take repeating it, blocked edges. So we have for every vertex in U, so there is size of U of them, we get at most I blocked edges. Right? So that means that F has size at most size of U times I. OK. So because of the diameter properties we will see soon in a moment, we will never take this I to be longer than log n log log n using the exercise. So at some point that will happen. But for now, let's just assume this is everything we need to do. We'll see it in a moment. So right? And how many edges are we allowed to forbid according to this property? So it's epsilon times the average degree. Remember, this is log squared times log log squared. And this guy is at worst 1 over log n, because we will stop this expansion at a half. So you get here log n times log log n squared. And you are allowed to forbid this many edges and still keep the same expansion as the robust sublinear expanders guarantee. Right? So this is actually the key place where I'm going to be using that this d of h is log squared n. So we'll be using it in a bunch of other places just to make things simpler, but the other places with a bit more technicalities, you can more or less easily get rid of them. But this is really the crucial place. I'll come back at the end and tell you kind of how you, at least a rough idea how you get around this issue. But most of the other argument actually works fine with log n, log log n, except this point. So here, we lose, at least for large sets, when epsilon is 1 over log n, we lose this 1 over log n compared to the d of h, and then we would not be able to forbid this many edges once we are kind of very large. OK, so just the conclusion is, so RSE property implies that the neighborhood in G minus F of U has size at least epsilon over 4 times the size of U. And note that any vertex here actually gets added to the rainbow neighborhood of I plus 1. Because we removed any edge which is not a witness for the growth of the thing. Right? So that was the whole point of F. Once we delete these edges, so these were our F edges, now every other edge is a color that's distinct from the path that comes there. So you can use it to extend your rainbow path and witness that this vertex now goes into the next rainbow neighborhood. Yes?
Why can't you have several rainbow paths contributing more blocked edges?
You can, but we only need to care about one, right? Because I need only one rainbow path to survive. And actually what you're saying is like one of the key things that lets you get to the log n, log log n, which is that actually you expect, because of how the process works, to have many rainbow paths here. And so that actually lets you kind of free up in a certain sense. I'm simplifying a lot, but I'll get back to it at the end. But it's a very good point. You can have many rainbow edges from here to here, rainbow paths. I just fix one, and I use that one. If you wish, I can actually just, as I wrote the definition, it says that so long as there is a path for which I can extend, I'm happy. Right? Because I don't really need all the paths to extend. I just need one to witness that this vertex gets added to the rainbow neighborhood I plus 1. Thank you very much. Any other questions? So what we just got is that these rainbow neighborhoods grow precisely as if we were just using normal neighborhoods in an expander, right? So this is precisely the kind of the thing that you were supposed to do in an exercise from Monday, to compute how long it takes you to get there. And it takes you log n times log n steps to reach more than a half, if you do it carefully. So that means that we reach in log n steps, so that this inequality is preserved throughout this process, more than half of the vertices. Okay? Let me write that. So, rainbow neighborhood at radius log n, and I probably need like a 2 there. Log n, log n. Around V, using all the colors, is bigger than n over 2. Is the conclusion of all of this. Right? They grow as if you just looked at usual neighborhoods. We know how usual neighborhoods grow. They grow precisely at that rate. So I guess I need also 2 there, but OK, so that looks very promising, right? So if we go back to the picture I just erased, we had our vertex, and we now grow rainbow neighborhoods, not the usual neighborhoods. But still, we reach in relatively few steps, we reach more than a half. OK? So let's try to rerun our strategy. So there's another one. Yes?
It's a 2, right? Not an I.
This?
Yes.
That's a 2, yes. I'm just being pedantic because if you do the diameter calculation, I think you get 1 plus, like actually maybe even 4 because I put a 4 there. So let's do 4. Let's do an 8. Why not? But yeah, please do point out things when my handwriting is horrible. This is why I'm writing in block capitals. So that's hopefully readable somewhat. OK, so if we run it from the other vertex, things look peachy, except does anyone see what the issue is? So we now find the rainbow path here, find the rainbow path here. We can reserve this one color edge at the beginning. It's not really a problem, right? We can chug it into the F. It's just one extra color. That's always forbidden. So what's the problem? Perfect, right. So they are rainbow as a path. This is rainbow as a path. But who tells us that they don't use some colors, some same colors? So we're kind of almost there. This morally tells you this is essentially end of the proof if you're using this stuff. Except there is this nonsense issue, which I don't really have a very clean way of dealing with. But actually, the way of dealing it is super instructive, I think, for how you use and what things show up when you work with these things. OK? But we need to deal with it somehow. So what's a natural way of dealing with it? Yeah? Yeah. Very good. But how do you choose which half and which half it is? Because somehow, once you start forbidding half of the colors, that thing will start to collapse. So you need to be a bit careful. You are on the precisely right track, but you need to be careful how you want to choose your sets of colors.
Can you grow the balls at the same time?
You can try, but the problem with these balls is that somehow, like, you know that this vertex has a short path that goes there that uses few colors, but you really don't know, kind of up until you reach it, which set of colors it will be. So you kind of reach things. So you can try, and I'm not claiming that no version of this argument works, but I don't know how to get that to work. So maybe if you add a few more polylog, but anyway.
So if you partition to disjoint color classes, it will not work?
So not universally. So you can cook up kind of, and this is some cheating way in which you can kind of, maybe your graph is an expander because exactly half of the colors, and the others are kind of doing something silly. They don't even connect your graph, or they just live on a small place. So they exist, but they don't really contribute anything to the expansion. And then, like, okay, first one's good, you have your thing, but the second one, you can't do anything in it. Yeah? Precisely, perfect. So what you want to do is you want to partition the color set randomly. So this is an idea that people who work with expanders, even usual ones, are very familiar with. It's called subsampling or partitioning or however you like. Expanders are very good at it usually. So if you have your good expander and you want to split it into two or you want to partition it into expanders, they're very, very good at this. And more or less the only or sensible way of doing that is usually at random. If they're strong enough, you will inherit kind of the right properties. So here we are doing something that's a bit unusual and that makes this a bit harder, but also makes it more illustrative, I think, is that our samples of edges are not uniformly random. Right? We're choosing colors at random. Colors are perfect matchings in our picture, so there's the dependencies between edges. So whatever you try to do from the usual partitioning point of view, and these expanders actually have an edge partitioning lemma. You can cheaply partition, if you split every edge left and right with probability half, you'll get two expanders with only a tiny bit worse properties there. Subsampling vertices is more difficult. We'll get to that point in the next, maybe last lecture, I think. But subsampling edges is usually OK, except here we're subsampling colors, which precisely cost you everything. So just to illustrate this idea, so we do still expect when you subsample colors that most edges actually expand OK, right? So most subsets expand OK. So suppose we have a subset U, right? And it has some number of edges going out. And let's ignore well, OK. So what can happen is that this set is incident to at most D colors. Right? We're not guaranteed to have more than D colors in our graph. Hypercube had exactly D colors. Right? So with probability kind of 1 over 2 to the D, and D is a polylog for us, or log close to log, or log squared, right? So this is something kind of close to polynomial. So actually small sets are fine, but for the union bound, you would want to run it over n, choose U many different subsets. When U gets even the tiny bit bigger, you lose any hope of the naive union bound working for this. And this precise thing is kind of a big annoying issue with this type of expanders. Actually, if you knew that your neighborhood is a bit bigger than kind of by a constant times U, you would start getting much better things. I mean, that would imply in this silly situation that you have at least more colors. So this is why in usual expanders, this type of things tend to be a bit easier because very often you can get away with just a union bound. For these guys, you need to work harder and you need to kind of get around, do some clever things. So I actually don't know how to prove that if you sample colors with probability half, you actually get an expander. It seems to me that it's plausible that it's true, and I don't see any counterexample to it. But what we have kind of to deal with this is we kind of get the same conclusions, but we need to kind of work a bit more carefully about it. So kind of really the key idea is going to be that we are not going to care about expanding all the subset, but just a relatively few of them. Right? So I don't care that my subsampled graph as a whole is an expander. I only care about my balls. And I... bad choice of words. And there is only log n of them, right? So that's way, way fewer than what you get there. OK, so neighborhoods, rainbow neighborhoods, yes. Very good. So this is very instructive what we did so far, and it's going to appear kind of heavily. But what we really want is that the same thing remains true when you work with a randomly sampled subset of colors of size half. So the rainbow neighbors, so let me call R is 10, let me actually try to get the constants right. 10,000 log n log n. And we want that the rainbow neighborhood of radius R around V with C sampled with probability 1/2, so I'll explain the notation in a moment, has size bigger than 2, n over 2, with probability bigger than 1/2. So this notation, if you have a set X, X of P is subset obtained by sampling elements of X with probability P independently. Okay, so that's just what I explained in words before. I want to take the color set with probability 1/2, and I want that this happens with probability bigger than 1/2. Okay, so why are we done if we prove this? Precisely, perfect, right? So the complement of this set of colors is also distributed as C1/2, right? So I use, if this happens with probability bigger than 1/2, by a union bound, I can ensure that both it and for its complement, I get this property. And then I use one of them from the left and one of them from the right, and now I get my two paths using these joint sets of colors, and now I'm happy. So let me just also switch a little bit so we don't have to, so just to not deal with this final edge, you can actually just expand once, so fix one vertex, and expand up to more than 1/2 from it using one set of colors, and to more than 1/2 using the other set of colors. And now actually the vertex that you reach from both sides, you can use, it gives you a closed rainbow walk, which has a rainbow cycle as a subgraph. Right? So we don't need two vertices, we don't need this final vertex there. So goal, if we have the goal, if goal holds, with probability bigger than 0, there exists an outcome C prime of this C1/2 process, such that conclusion holds for both C prime and C prime complement, which is also distributed as C1/2. And now, we just do our usual, well, it's slightly twisted here because we are working in the, from one vertex, but other than that, it's mostly the same. So we'll get rainbow neighborhood of radius r around V using C prime. Is bigger than 1/2, and rainbow neighborhood around r, radius r around V, using this C bar complement. So the other colors are both bigger than 1/2 with probability at least 0. So there is an outcome where this happens. And then just take the rainbow path from, so find the vertex that lives in both of them, find the rainbow path that goes in one, find the rainbow path that goes in other. I'm cheating you slightly here, so you can think why I write what we do. So pick a common vertex, find R1 rainbow path using colors in C prime and R2, so a common vertex U, and then this one is a VU rainbow path. Using colors in C without C bar, concatenate, and get a closed rainbow walk. So what am I cheating about? Something very silly. So what if U is equal to V? Right? We know that V is in both of these sets, just trivially. So if you get a UV, that's a trivial walk. It doesn't really do anything for us. Right? So what we need here is technically this. And nothing really changes anywhere, so I will pretend that I'm happy with n over 2 just to not have this +1 trailing around everywhere, but technically you do need to take into account the V. Very good. So now we're left with the goal. And I think I'll probably finish the goal only next time, but let me try to tell you a rough idea of what's going to happen. So what we're going to use is a sprinkling method, and we're going to use it in a way that Tomon actually first used for these problems. It cleans them up a lot. So there are other ways of doing it, but then we'll see one a bit later again. But for now, we will use the sprinkling method. It's also a very nice tool and method to see if you haven't seen it before, and also it's used kind of nicely here. So as I kind of shown in that picture, the just direct sampling is a bit bad, right? If you try to sample with probability 1/2, not all subsets will survive. Now I said, okay, I only care about these rainbow neighborhoods that I get as the things grow, right? So that's a few sets, but I don't really know that those sets a priori, right? They are outcomes of that random sample. And how do you deal with this type of issues? Well, one of the cleanest ways is just, instead of revealing all of your probability at once, just do it in stages. So we're going to split our random edges into kind of smaller random subsets that we are going to reveal one at a time. And after I reveal the first I of them, I claim we are still going to grow as we should, as like that growth rate is telling us. And I'm just going to use the new batch of colors to get the extra growth. And now the sets are actually specified perfectly, because I revealed the first I random sets, and only then look at the I +1. So let's set this up. So let P be equal to 1/4R, where R is that radius which I wrote somewhere there. And let C1 prime, C2 prime, up to CR prime all be C sampled with probability P, distributed as C probability P. Okay, then what's the, if we look at C1 prime union CR prime, how is this distributed? Well, it's also some C of some P prime, and this P prime is this usual sprinkling calculation. So the chance that you didn't pick an edge is 1 minus P to the power R, and then you do some numbers, blah, blah, blah. But roughly speaking, we have R of them, and at each stage they had 1/4R, so you sort of expect with probability 1/4. And if you do these numbers, you'll get that B prime is less than 1/2, which is what we sort of care about. it's not quite 1/4, it's something slightly shifted around it. It's closer to 1/4 than a half, but we can waste that. Okay? So do that computation if you've never done it for the sprinting stuff. Good. So that means that this is going to be our final random set. And now let me define Ci to be C1 prime union up to Ci prime. So the colors that we revealed up to stage I. Let me write now the lemma that we want instead of that goal. Let the goal survive for a bit. Right, so now what I want is that rainbow neighborhood of radius I, or I plus 1, started at V, using colors I plus 1, has size that is bigger than epsilon over, I think in the end it becomes 128 or something like that, times the size of the rainbow neighborhood of I when we take it from V and Ci. So this is something that you should find surprising, or at least I did initially, because what's happening here is, so this is just some subset, right? Now we're subsampling colors with probability 1/log. And I'm saying that still you expand as if we just weren't doing anything. And here is really where this robustness thing saves you a lot, because actually each of these vertices has plenty of ways of going back. So even though you're sampling, actually in expectation, everyone survives. Or, well, some fraction, constant fraction of them survive. Okay? So this is something that we will do. But this is really the key lemma. And there is also a caveat, or this is bigger than a half, and just because we don't want to expand bigger than. Okay, so now this is the only thing that we need to prove, right? And is everyone happy that if we do prove this, also I'm lying slightly, these are random sets, right? They're not explicit sets. So this should happen with some probability. And what probability do we want? Well, we want enough probability that as we do these stages, we can do a union bound. And how many stages do we do? If it grows the same way as it did before, it's still just log n, log n times that number, so maybe 1,000 log n now. So we need that this happens with probability bigger or equal than 1 minus 1/1,000 log n. Actually, I guess I can write 1/8 times radius, and radius is already some 1,000 log n. Right, because we do radius stages of this, and I claim that by this point we'll reach this more than a half. So also formally how this is actually done is you reveal what happens for the first CI, and then for any outcome that satisfied the current growth rate, you want that the next step proceeds in the same way. So the only randomness in this inequality is what happens in the reveal of the final color set Ci plus 1 prime here, which happens at that probability. So we'll prove that lemma next time. It's a nice trick which pops up in lots of different places, and it's not that hard to prove. And also, if you want, you're welcome to think of how to finish it. So let me stop here today and have a great break in the afternoon.